Yeah, welcome. So we are discussing about classical planning. So let's continue our discussion. So in the last lecture we have discussed like how planning is done for a cargo based problem. So we'll be discussing one more examples of this kind. So this example is something called as blocks world. So where we want to move one block on top of another block, something like that. So this is this. Let us assume this is the start state. In the start state, say this is the table. On table there were three blocks. There is a block B which is on the table directly, and there is a block A which is also on the table, and there is block C which is on top of A. But this is the goal state we want. The block C should be on the table, and block B should be on top of block C. Block B should be on top of block C, and block A should be on top of block B. So this is the goal state we want to achieve. Now how it can be done through the planning problem, that's what we are going to discuss. So this is one example. We'll not be discussing the same example. We'll be taking some other scenario, and we'll be discussing like how it can be achieved through planning, and how it can be, and how these list of commands or statements can be represented using stripes. That's what we are going to discuss. So this is our problem definition. This is our initial state. Our initial state is on a comma table, that is block A is on the table. So this is the initial state. So this is the table. So block A is on table. So let me draw a bigger table. So this is the initial state. So this is table. Let us assume this is table on A comma table, which means block A is on table, and on B comma table, which means block B is also on the table. This is the table, right? And on C comma table, which means block C is also on the table. Okay. And where A is a block, and B is a block, and C is a block, and clear of A, which means nothing on top of A, right? And clear of B, which means nothing is on top of B, and clear of C, which means nothing is on top of C. This is the initial state. Let me call it as IS. Now our goal state is on A comma B and on B comma C. See, goal state you should be a little careful. So goal state should be what? On A comma B. So let us try drawing, which means A should be on B. So B is here, then A is here. Okay. Then and on B comma C. On B comma C, which means what? B should be on top of C, which means C should be here. So totally it means that C is only resting on the table. On C you should have B, and over B you should have A. So this is the scenario. Okay. So uh, so basically our goal state is something like this. That is, C should be placed directly on the table, and on top of C we want B, right? And on top of B we want A. This is the goal state. Okay. Now how can we achieve this goal state? That is the question. And what are the typical actions that we can perform? So this is one action we can perform. The action is move B comma X comma Y, where B is a block. So move B comma X comma Y means what? Where B is a block, and currently B is on X, and B is currently on X. Now you move B from X to Y. That is what it says. Okay. Now what is X and Y? X and Y can be either a block or a table. Okay. X and Y can be either a block. They can be either some block, or it can be a table, right? So move B comma X comma Y means move the block B, which is currently placed on top of X, to Y. That is the meaning. So for this command, what is the precondition? Or for this action, what is the precondition? So there will be some preconditions for every action, as we have discussed in the last class. So for this action also there is a precondition. What is the precondition? First of all, B should be on X. Then only you can apply this command. Okay. And on top of B there should be nothing, right? See, let us assume there is something X, on top of X we have B. but nothing should be on top of B. Then only you can apply this command. If already something C is on the top of this B, then this command you cannot apply, because it is applicable only to the topmost block. So first is B should be on top of X, and B should be clear. There should be nothing on B. Okay. And now where are you going to move B? B we are going to move on to X, Y. We are going to move B from X to Y. So there should not be anything on top of Y also. So clear of Y. Okay. And B should be a block, and B should be a block, and B should not be equal to X, and B should not be equal to Y. That is, these things should not be same, and X also should not be equal to Y. If these conditions were satisfied, then we can move the block B from on top of X to on top of Y. Okay, so that's the uh, that is how this action is defined. So once you apply this action, suppose if this precondition is satisfied, and if you are applying this action, then what will be the result? The result will be something like this. After applying this action, the block B will be on top of Y. Block B will be on top of Y. X will be cleared. There is nothing on top of X, and no more B is on X. That is not on B over X. Okay, and not clear of Y. Previously Y is clear. Now Y is not clear. So after applying this action, what happens? B will go on top of Y. B will go on top of Y, and X will be cleared. There is nothing on the top of X. Okay, and B is not on top of X, and Y is not clear. This is not is here. Okay, and Y is not clear. So this is the effect of applying this particular action. Similarly, we have one more action. This action is to move something to the table. So we have an action something like this. Action move to table B comma X. Move to table B comma X, which means there is a block B which is on top of X. Now we are saying that move this block to the table. That is what it says. Move this B to table. Now for applying this action, what is the precondition? First precondition is B should be on X. Okay. And next is there should not be anything on top of B. So B should be cleared, and B should be a block. B should be a block, and B should not be equal to X. Both B and X should not be same. First is B should be on top of X, and B should be cleared, and B should be a block, and B should not be equal to X. Right? If you perform this operation, then what will be the effect? If this precondition is satisfied, and if you perform this action, the effect will be B will be on table, and X will be cleared, and B is not on X. Okay, so this is the result of this particular action. Now these are the something like syntaxes for various action. Now this is now for this our problem. This is our problem. For this problem, what are the sequence of actions we need to perform to reach the goal state? That is the question. Okay. So first, what should we do? Now in our case, everything is on the table. So you need not apply this. Move to table is not required. First, we should move B to the top of C. Okay. We should move B to the top of C. So for that, what command we have to use? Move B comma, move the block B. Move the block B. Currently, where is the block B? Currently, the block B is on table. So move the block B from table, right? Okay. Move the block B from table to where? It should be moved to C, right? So now the block B, which is currently on top of table, will be moved on top of C, right? Next, another command, what should we do? Move the block A, which is currently on table, to block B. So this is first step. When you execute this step, block B will come over C. Then you execute the second step. When you do the second step, block A will come over B. Right? So these are the two steps which we do. Okay. Fine. But here there is a small catch. What is the catch? See, you see this particular action move B comma X comma Y. After applying this action, what happens? B is on top of Y, that is fine. But it says that clear of X. Clear of X means what? Nothing is on X. But here, even after moving B to C, table will not be get cleared, right? Something will be on the table, right? So now we are defining now we are redefining the meaning of clear. So so previously what we assumed, clear means nothing on top of something. Okay. So mm, so here we should redefine the meaning of clear. So clear means it is not that uh, nothing is on top of the table. It, uh, something can be there, but this block is cleared. Okay. Something can be there, but so so this clear of b, we should not interpret this way for table. So that's the point. So clear of b can be interpreted as nothing on top of a b c for block, but it should not be interpreted that way for the uh, for the table. Okay. So clear of table means, it means that there is some space on the table. That is the meaning. It's not that totally it is free. There is some space on the table to accommodate something, some other block. That is what it means. Are you getting? So this clear of b, we should interpret in a different way. But otherwise, this is the rule we have to apply to reach this particular goal state. Okay, fine. Okay. So now let us discuss something about heuristics. So 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 let us see like how the planning can be done in a state space search. So state space search means if you take any problem, it has it has it has a state space, right? It can be in a different states at a particular point. I mean, throughout its uh, the possible states of the problem can be so many, right? Okay. So the straightforward approach for any planning problem is to solve by using state space search. Okay. For solving by using state space search, we can follow two types of technique. Either we can follow forward search or we can follow backward search. But all these techniques, forward search and backward search, they all depends on effective heuristics. This technique will work better only if you have a good heuristic. If you don't have a good heuristic, they won't perform better. So it all depends on the heuristic function which you will be using. So first, let us discuss briefly about forward state space search. The forward state space search is otherwise called as progressive planning. That is, in a state space search, if you want to apply planning, and if you apply forward state space search, and that is called as progressive planning because it moves in forward direction. So forward means we start with some initial state and then we move on to the next state, so on and so forth until you reach the goal state, right? So this is how the forward state space algorithm proceeds. It starts with the initial state, it performs some sequence of actions until it reaches the goal state. So we define the problem in using, if you want to solve the problem using forward search, using forward state space search, then we'll be representing the problem something with initial state, with set of actions, and with goal test. So what is the initial state and what are the actions that can be done, and depending on the current state, appropriate action will be chosen, and and the problem will move from one state to another state, and this process will be continued until you reach the goal state. Okay. So after reaching the goal state, after reaching every step, after reaching from one state to another state, we check whether the goal is achieved or not, right? The step cost of each action is typically one in strips. In strips, the step cost of each action, it is initially you are in the initial state, and when you move to the next state, this now the current state is this. So there is a cost involved in moving from one state to another state. Okay. So this is one step, and the step cost is typically it is one for strips. Okay. But the problem with the forward state space search is it is too inefficient to be practically implemented, because it has many, it will perform many irrelevant action, and that is, it may perform lot of action which is not at all relevant to reach that particular goal state, right? So basically it does not address the irrelevant action problem. uh, the approach also quickly bogs down without a good heuristic, and And if you don't have a good heuristic, this forward state space search, it won't work in a proper way, and it won't provide a good result also. So these are the drawbacks with forward state space search. Hence, mostly we'll be using backward state space search. In backward state space search, we start with the goal state. We start with the goal state and we travel in the backward direction, right? Say for example, let us take this problem. The goal here, the goal in a 10 airport air cargo problem is to have 20 pieces of cargo at airport B, right? So this is the goal. The goal is what? Let us consider a scenario where there are 10 airports. You have 10 airports, okay, and there are some set of cargos. There are some 20 cargos. These 20 cargos are splitted in different places of these 10 airports. Some cargo are in first airport, some are in second airport, some are in third airport, so on and so forth. Some are in 10th airport. But our objective is to have all the cargos, all the 20 cargos in airport B. This is the goal. So here, this is our goal state can be defined something like this. At C1, B, which means cargo 1 is at airport B, and at C2, B, which means cargo 2 is also at airport B, so on and so forth at C20, B, which means cargo 20 is also at airport B. So basically, we want all cargos in the airport B, right? Now, if you see, this is actually this entire thing contains. So this is our goal state. This is our goal state, but this can be treated as it has multiple sub goals. For example, this is one sub goal at C1, B is one sub goal. At C2, B is another sub goal, so on and so forth. We have 20 such sub goals. So let us take this alone at C1, B alone. So this is the final conclusion. We want the cargo C1 to be in the airport B. Now we are discussing backward search. In backward state space search, we start from conclusion and then we backtrack. Okay, and then we identify the appropriate moves. If the cargo C1 should be at airport B, then what should be the previous state of that? If you want cargo C1 at airport B, then what should be its previous state? Previously, if what state is there, then it can reach to this particular state. The previous state will be something like this at C1, P, B, which means what? The cargo C1 is at plane B and the plane B is at airport B, right? Okay, so or instead of at, we can use here unload. Okay, that is previously which step will lead to this step. Previously, if you perform what action, that will lead to this step, that is unload of C1, P, B. So which means what? Unload the cargo C1 from a particular plane P in the airport B, which means already the cargo C1 is in the plane P and the plane P is in the airport B. Only if this situation is there, then only this is possible, right? So its previous step should be something like this. Cargo should be in plane B and plane B should be in airport B. If that is the case, then we can perform the unload operation and we can move the cargo 1 from plane P to airport B, right? So like this, we have to backtrack. Now again, you have to see like if the cargo should be in, if the cargo 1 should be in plane P and airport B and the plane P should be in airport B. If that is the case, then what should be the previous step? The previous step may be something like fly. The particular plane may have to fly from one location to another location, so on and so forth. Like that, we we go back and find out what are the relevant actions to be performed. So compared to the forward search technique, this is much better because here we identify only the relevant actions and we ensure that those actions will be done. So basically we start with the goal state. From the goal state, we check like if this is to be done, then what is to be done? Then do that. Similarly, if this is to be done, then what is to be done? So on and so forth. We backtrack and identify the route. Then from that point onwards, we keep doing everything, and finally we reach this goal. Okay. So like that, it should be repeated for all the sub goals. So this is how basically backward state space search works. So backward search space is also called as regression planning, because we are moving from the conclusion to the initial state. Okay. So in addition to insisting that the action achieves some desired literal, the backward search should ensure that it is not that it achieves some desired literal, but it should also ensure that it is not undoing any desired literals. Okay. So achieving desired literals means what? Now these are our desired literals at c1 comma b, at c2 comma b, so on and so forth, at c20 comma b. All these are our desired literals. So we want to achieve all these things one by one. So the backward search should ensure that uh, these desired literals are achieved. Okay. But at the same time, it should also ensure that it is not undoing any desired literal. Say already, say let us assume already this is achieved. Okay. This is achieved already. Say that now when you do something else, this got undone, which means it becomes unachieved. That should not happen. So that is what it means. So the backward search should ensure that the the desired literals are achieved, and also it should ensure that it is not undoing any desired literals. Okay. So ensuring this is called as consistent. An action that satisfies this restriction. Which restriction? The restriction of ensuring that desired literals are achieved and none of the desired literals are undone. That is what is called as being consistent. Okay. So backward state space search should be consistent. Right. So this is in brief about backward state space search. But the problem is neither forward or backward search is efficient without a good heuristic function. They all depend on the good heuristic function. Without a good heuristic function, actually they can't perform in a better way. Right. So basically, we need an admissible heuristic. So you know what is an admissible heuristic? An admissible heuristic is the one which does not overestimate the goal state. It should underestimate. It should not overestimate. Okay. So there are basically two approaches that can be tried to arrive at an admissible heuristic. So the first method is to do by relaxing the problem. The first method is by relaxing the problem, which we already discussed in some cases, like 8 puzzle problem and all we have discussed, like how what you call how the how a heuristic can be identified. So an admissible, so the point here is forward and backward state space search are not efficient unless and until you have a good heuristic function. Now, if you want to have a good heuristic function, so the heuristic function should be admissible. That is, it should not overestimate the goal state, it should underestimate. Now, how will you create the admissible heuristic? That is the question. Admissible heuristic can be created in two ways. Either by relaxing the original problem, so that is one way. And the second method is by performing divide and conquer technique. That is, divide the problem into several small problems and solve the individual problems and take the sum of that. Okay. So when you do that, when you divide a big problem, so you have a problem, and when you divide the big problem into several small problems, and when you do like that, okay, you should also ensure that these so basically these are sub goals. So this is our original goal. Problem in the sense this goal. Problem solving problem means what? Achieving goal. Okay. So we are dividing the problem into several sub problems. It means each of the sub problem will have a sub goals, right? And then we are going to combine all these things. But this is applicable only if all these sub goals were independent. That is, they should not depend on each other. Okay. So this is applicable only if all these sub goals were independent. They should not dependent on each other, right? That is, none of this. For example, P1's goal should be different from P2's goal, so on and so forth, and everything goal should be different. Okay. And also their precondition should be different. Everything should be different. Then only it is possible. Okay. So we'll discuss more on that. But as of now, understand that there are two ways to go get with a to identify a good heuristic. First method is by relaxing the problem. The second method is by using divide and conquer technique, by which we divide the problem into several small problems, and then we solve the problem. We solve the small problems, and we combine all the small problems result, and by that we form the heuristic. But this is possible only when all the sub goals were independent. So we have an assumption here which is called as sub goal independence assumption. Okay, fine. So now let us discuss some heuristics. Let us discuss some heuristic techniques. We'll be discussing some 3-4 heuristic techniques. This is one particular heuristic technique which is called as ignore preconditions heuristic. So we have discussed that basically there are two ways to identify a good heuristic. The first method is by relaxing the original problem. The second method is by divide and conquer technique. Okay, so this actually comes under first method. This is here we are relaxing the original problem. In the original problem, whatever the problem we have discussed so far, say for example the cargo problem, or uh, uh, the cargo problem or the blocks problem, there are, if you want to apply any action, the precondition should be satisfied. Without satisfying the precondition, you cannot apply the action, right? But this, to identify the heuristic, to identify a good heuristic, one of the rule to identify the good heuristic is what? Relax the original problem. So here this relaxation we are doing, what relaxation? Ignore the precondition. So we are doing this not to solve the problem, but only to identify the heuristic. Ignore precondition. That is, when you want to apply any action, you don't check for any precondition, just apply the action. That's what it says. Drop all preconditions from actions. Okay, every action becomes applicable in every state. So if you drop all preconditions, then every action is applicable in every state. So any single goal fluent can be achieved in one step minimum. Are you getting? So now, for example, if the solution is, if this is the solution we want, at cargo 1 should be at airport B, and cargo 2 should be at uh, airport B, so on and so forth. Cargo 20 also should be at airport B. Now there is no precondition. Any action can be achieved at any time. So at every step you can achieve at least one sub goal. Okay, because directly you can apply that action, uh, uh, like load the cargo or fly the flight, something like some rule you can apply at every step. So every step you can make sure that at least one goal is satisfied, provided if the appropriate action is available, right? So basically here what we are doing, we relax the actions by removing all preconditions and all effects except those that are literals in the goal. So we are not only relaxing the precondition, but also we are relaxing the effects. Effects also we are ignoring. Okay, we are only bothered about the effects that are connected in the goal state. So only that effects we keep, other effects we ignore. Okay, are you getting? So when you apply an action, say currently you are in one state, when you apply an action, obviously we will move to a new state, but in the new state, whatever the changes happens we ignore, but we keep only those literals which are in the goal state. So this is what it means. Okay, so so by doing like this also you can identify a good heuristic. So see, if you are wondering like how it is possible, if you recall the 8 tiles problem, we have discussed like something like this. Say there are 8 tiles, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have discussed like say this is initial state, this is initial state, and this is goal state. So we have discussed two types of heuristic, if you recall, right? The first heuristic is number of misplaced tiles, 1, 2, 3, 4, 5, 6, 7, 8. So in that case we just count how many tiles are misplaced. 1 is not misplaced, 2 is misplaced, 3 is misplaced, so on and so forth we count number of misplaced tiles. And the second is number of the Manhattan distance, the Manhattan distance of the tile. For example, 2 here, it is here, the goal state it should be here, so it is 2. Like that we count. So this is also what, so that is also what a relaxed version of the problem. Generally you cannot move to from here to here, but this is a relaxed version. We are assuming that you can move. We're getting. Similarly, in the first case, we are only counting the misplaced tile, which means we are directly we can move any tile to anywhere. That's what we are assuming, right? So those heuristic also, it's nothing but is an example of relaxed version of the problem. So why we are doing like that? Because a good heuristic should underestimate. So when you relax the problem, automatically it will become an underestimate, right? I guess you are following. Okay. So 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 when you ignore the preconditions of a problem, you will get a heuristic, and surely that will be a good heuristic. And creating a heuristic in this style is basically is an example or instance of set cover problem. Okay, it's an instance of, it's a type of problem. It is one example of that type, set cover problem. So now we'll be discussing another type of heuristic, which is called as ignore delete list heuristic. Ignore delete list. So in the first heuristic, we have ignored preconditions. There is another way of creating a good heuristic which says that ignore delete list. What is delete list? So delete list basically contains the list of literals which is to be removed, which is to be removed. Okay. So assume that all goals and preconditions contain only positive literals. So here we assume that the goals and preconditions only contains the positive literals. Removing the delete list from all actions. That is, remove all negative literals from fx. So if you recall, when you apply some action, the effect will have positive literal and also negative literal. For example, if you go back here, if you apply this particular action move comma b comma x comma y, if this precondition is satisfied, then this action can be applied. Now the effect, if you see, the effect contains positive literals and also negative literal. This is a positive, this is positive, but these two are negative ones. So ignore negative literal, what it says in the sense, from the effect you ignore the negative ones, don't consider that. Okay. So it means that after applying the action, we keep this on b comma y, we will add to the knowledge base. Clear x also we add, but these two things we won't remove. So already this is there, that also will be there in the knowledge base. On b comma x also will be there in the knowledge base. Okay. Clear of y also will be there in the knowledge base, right? So so why we are doing like this? Because we are keeping every option open, right? We are keeping, because we want to identify a good heuristic, and good heuristic can be identified by relaxing the original problem. Now if you may ask, this is not correct, this is not correct, but this is something like cheating and playing the game. Okay. So cheating and playing the game is also what, it's a relaxed version. So when you relax the problem and if you reach the goal, that can be taken as the heuristic function. Are you getting? So that's the key, because our heuristic function should underestimate. How you can identify an underestimated heuristic function? You, for that you have to relax, some of the rules. Okay. For identifying the heuristic function we are relaxing, not for solving. Again, then we'll using this heuristic function we'll solve, right? So that's the whole point here. So ignore delete list, what it says in the sense, after applying a particular action, the effect will have positive literals and also negative literals, but here we just ignore the negative ones, right? So the relaxed problem leaves us with with a simplified. But still no, the relaxed problem, but the, okay, so this is the so here we are discussing basically the drawbacks of these heuristic techniques. So okay, it is true that the heuristic technique, it is actually simplifying the problem. So it is really simplifying the problem uh, because we are relaxing the original problem, but still it is expensive. But still it is, even after simplification also the problem is expensive. So here is an example for that. Because most of the problem has this many states, they have more than 10 to the power 100 states. Okay. And even if you relax, the number of states is not going to reduce much. The number of states is not going to reduce much. Okay. Hence, so if the number of states are less, if originally the number of states were less, then these kind of heuristics will work. But already our original problem has so many states. Hence, even this heuristic functions which we are creating after after relaxing the problem is also is also not good enough. That's the point. Okay. Hence, we are looking for some other technique which is called a state abstraction. Which is called a state abstraction. So basically, it is a many to one mapping from states in the ground representation of the problem to the abstract representation. So here, so this is also you can, the state abstraction is also one type of heuristic. Okay. So these, whatever the heuristic which we discussed previously, these are not applicable for the real world problems which we are discussing. The reason is they are relaxing the problem and they are identifying the solution. But our problem contains, see, this many states. So our problem contains states of this order. Hence, even after relaxing the problem also, they are still expensive. After simplifying also, they are still expensive. Hence, it's not practicable to use these heuristics. Hence, we are going for another technique which is called a state abstraction. This is also a heuristic technique. Here, what we are doing in the sense, we are abstracting the problem itself. We are representing the, we are trying to represent the problem itself in an abstract level. We are not going to represent the problem in a detailed level. Rather, we are going to simplify the problem itself. So now, after simplifying the problem, it becomes a uh, it becomes a relaxed version of the problem. So that's the whole point. Okay. So the easiest form of state abstraction is to ignore some fluence. So this is one way to perform state abstraction. State abstraction means you reduce the problem size. Don't keep it a big size. Reduce the size of the problem. So one method, what it says in the sense, they ignore some fluence. Fluence means some objects or some what do you call uh, some objects or some entities that were used in the problem can be ignored. Okay. So let us have one example. Let us consider this example: an air cargo problem with 10 airports, 50 planes, and 200 pieces of cargo. So this is an air cargo problem. There are 10 airports. We consider 10 airports, and there are 50 planes. These 50 planes can be in any one of these 10 airports, and there are 20 pieces of cargo, 200 pieces of cargo. And these 200 pieces of cargo, it can be on any of these airport or on any of these flights. Okay. And these flights can be on any of these 10 airports, right? So each plane can be at any of the 10 airports, and each package can be either in one of the planes or unloaded in one of the airports. Okay. So this is the scenario we want to represent. Each of these plane can be on any of these airports. Each of the 50 planes can be any of these 10 airports. Each of these 200 pieces of cargo can be on any of these 10 airports, or it can be on any of these 50 planes. Now, this problem, it contains how many states? It contains this many states, 50 to the power 10. That is, the 50 planes can be on any of the 10 airports. 200 to the power 50 plus 10. That is, the 200 pieces of cargo can be on any of these 50 planes or any of these 10 airports. So it contains this many states. Okay, 10,155 states, which is quite high. Now, let us see like how this problem can be relaxed by performing state abstraction. So, so here we are going to perform abstraction. So this is an abstract representation of the problem. Consider a particular problem in that domain, right? In that domain in which it happens that all packages are at just 5 of the airports. So here package means cargo. Let us assume that all these cargos, all the 200 cargos, can be in only 5 of those airports. Originally, there are 10 airports. Out of these 10 airports, let us assume that all these cargo can be only in 5 of those airports. And all packages at a given airport have the same destination. What does it mean? Say let us assume these 5 airports are A, B, C, D, and E. Okay. So these, all the cargo will be distributed only in these 5 airports, right? Okay. Let us assume, so, and also we'll assume that all the packages at a given airport have the same destination. So if there are 20 packages, say there are 25 packages in B, then all these 25 packages will have the same destination. That is if the destination of any one of the package is E, then all the 25 destination also will be E. That's the point. If there are say 50 packages in airport D, then all these 50 packages will have the same destination. So let us assume it is A, so on and so forth. That's what it says. Okay. So this is a relaxed version of the problem. Here we have abstracted the problem. The original problem is of bigger size that we have abstracted. So after performing this abstraction, now it has only this many states. It is 5 to the power 10. Okay, it is 5 to the power 10 and 5 to the power 5 plus 10. It has only 1017 states. So compared to this 10,155 states, the states were reduced very much. Okay, a solution in this abstract state space will be shorter than the solution in the original space, right? Because this is abstract representation of the problem. Hence, the solution in this shorter in this abstract space will be shorter than the solution in the original space. Okay, but the abstract solution is easy to extend to a solution to the original problem. But using the abstract solution as a heuristic, using the abstract solution as the heuristic function, we can find the solution for the original problem with less number of steps. That is the key. Are you getting? Now, why we are doing this abstraction? We are doing this abstraction and we'll solve this problem. We'll solve this problem in less number of steps. This will, and after solving this problem in less number of steps, that will be using as a heuristic function to solve the original problem. Okay. When you use that as the heuristic function and solve the original problem can be solved in the less number of steps. Are you getting? So basically, why we use heuristic? We use heuristic function to achieve to reach the optimal solution. So this is the key point here. Okay. So initially we have discussed that there are two ways to create heuristic. One is by relaxing the problem. So these are the techniques we have discussed for relaxing the problem and creating the heuristic. First method is ignore preconditions heuristic. Second is ignore delete list. And third is by performing state abstraction. Right. The second method of identifying a good heuristic function is to decompose the problem. That is divide and conquer we have discussed. So basically decompose the problem into several small problems. But in that case, the small problems will have sub goals. All these sub goals should be independent. Okay, they should be independent. So the key idea in defining the heuristic is decomposition. You decompose the problem into several small problems, dividing a problem into parts, solving each part independently, and then combining the parts. Okay. Divide the problem into several small problems, P1, P2, so on and so forth up to Pn, and then solve all these individual problems and then combine the parts. Okay. So here we have an assumption, and that assumption is called as sub-goal independence assumption. That is, we assume that all these sub-goals are independent of each other. Okay. So then only this technique will be effective. Only if they are independent, it will be effective. The sub-goal independent assumption is that the cost of solving conjunction of sub-goals is approximated by the sum of the cost of solving each sub-goal independently. So sub-goal independence approach, what it says in the sense, you solve all these problems independently and then sum up all these things. And also we assume that all these problems are independent of each other. That is, they are not no way dependent on each other. That is, everything has its separate set of goals, and also every problem has its own preconditions. None of the preconditions of each problem should match. Okay, none of the preconditions of any two problems should match. So let us discuss with one example for more clarity. Let us assume that for a particular problem the goal is given as g, okay, which is subdivided into like this, g1 g2 up to gn, right? Okay, where g1 is achieved by solving the problem P1. Okay, G2 is achieved by solving the problem P2, so on and so forth. Gn is achieved by solving the problem Pn, right? So let us assume the cost of P1 is represented as cost of P1. That is, the cost of reaching this goal G1 is through by solving P1 is represented as cost of P1. Similarly, the cost of achieving the goal G2 by solving the problem P2 is represented as cost of P2. Okay. So this cost of PI is a heuristic estimate. So for every problem we have a cost, right? For P1 we have a cost, P2 we have a cost, P3 for everything we have a cost. So each of this cost is a heuristic estimate. That is this how this cost is achieved is by relaxing each of the G1. Okay. By relaxing the goal state, we have achieved the cost. Hence, it is a heuristic estimate. But now for the whole problem, we have to find the heuristic. So what we can do is you can take the maximum of all the cost of PA. So you have all cost of P1, cost of P2 up to cost of Pn you have. Okay, from all these costs you take whichever the cost that is maximum. One of that cost will be maximum. Take that as the heuristic function. Now if you take that as the heuristic function, surely that will be admissible heuristic. There is no doubt in that, because you are taking only one cost, but your objective is to solve the whole problem. You are taking one cost which is highest cost. That's not a problem, and that one cost will no way will match with the cost of all problems. Hence it will be an underestimate. It won't be overestimate. As it is an underestimate, it will be an admissible heuristic. Okay, but the problem is, in practice this estimate may be too low. See, it should not be, even though we say that an admissible heuristic should underestimate, but it should not underestimate too much. If it underestimate too much, then also it will have a number of steps. Number of steps will be more. Okay, so too much underestimating, it should underestimate, but it should not underestimate too much. Okay, say for example, your objective is to reach, say this is initial state, your objective is to reach somewhere to B, which is of 100 kilometers. Now you are using some heuristic function h of f. Say that h of f is saying that B is at location 80 kilometers. Actually, that is good. That is a good heuristic, because it is underestimating, but it is not underestimating too much. It is saying that it is 80. So as long as 80 kilometers reach, you won't worry. You will keep on travel. After 80, you will check whether you have reached B. No. Again, you apply the heuristic, so on and so forth. So this is actually, even though it's underestimating, it's not underestimating very much. But say that you have another heuristic function h of f2. So this is saying that initially when you start with A, it is saying that the goal is at 20 kilometers. This is underestimating, but it's too much underestimating. Now you will go to 20 kilometers, you will stop. Again, you will apply the heuristic. Once again, it will say 30 kilometers. Once again, you apply the heuristic, so on and so forth. Basically, it increases the number of steps. So the heuristic function should underestimate, but at the same time, it should not underestimate too much. So in this case, if you take the cost of PI for all the problems, and if each of the cost of PI represents the heuristic estimate, and if you take the maximum of those, that will be surely an admissible heuristic. But in most cases, this heuristic may be too low. This heuristic may be too low. So that's the problem. Hence, what can we do? So can we sum up all these things? So you have so many PI. So can we sum up all this? Can we do cost of P1 plus cost of P2, so on and so forth, up to cost of Pn? Can we do that? That's the question. Okay. So if you do, sometimes if you do that, it will become an overestimate. Okay. Sometimes if you do this, it may become an overestimate. So could we sum the cost instead? For many problems, that is a reasonable estimate, but it is not admissible. So admissible means, so it is not admissible means what? It becomes overestimate. Okay, but we can sum up. Two cost GI and GJ. So GI means it's GI means cost of PI. So we can sum up cost of PI with cost of PJ under this condition. What condition? If PI and PJ are really independent. If PI and PJ are really independent, then they can be added. Independent means what? If the effect of PI leave all the preconditions and goals of PJ unchanged, then PI and PJ were independent. Are you getting? So if the effect of PI, so PI is one particular goal, right? The effect of PI should not impact the precondition or the goal of PJ. If PI is no way impacting the precondition or goal of PJ, then PI and PJ are independent. In that case, the cost of PI and cost of PJ can be added. Okay. So the point is, out of all, so we have P1, cost of P1, cost of P2, up to cost of P20. Out of all those, you identify which are independent. So with P1, you check like P1 and P2, is the effect of P1 is changing P2 or not? If it is not changing, we can consider that. Otherwise, we cannot consider. Like that, we have to take only those PIs which are independent. Independent in the sense their effect should not uh, sh- their effect should not change the preconditions or goals of the other problems. other sub problems. If that is the case, they can be added, right? So you identify all such PIs and add, then that will be a good heuristic. That will be a good heuristic, and also it will be admissible. So that's the whole point. Okay. So these are the two ways in which heuristic can be identified. But still, uh, uh, but, but even though you identify heuristics like this, but even after that also, even after relaxing the problem also, uh, for most of the real world problems, still the problem size will be very huge. Hence, uh, hence it is not advisable to go with heuristic techniques, especially in case of planning problems. So we'll be discussing basically some other method to solve the planning problems, which is called as planning graphs, right? So that we'll be discussing in the next lecture. Now let us stop here. Thank you.